Look up at the night sky. See the stars move across the sky. The moon and the sun do the same thing. They rise and set. It's not surprising that ancient peoples viewed the earth as fixed, and all celestial objects revolved around us. The ancient Greeks, such as Plato, Aristotle, and culminating in Ptolemy, constructed a cosmology with the earth surrounded by a number of celestial spheres that rotated around the earth each day. There was a sphere for the moon, one for the sun, one for each planet, and one for all the fixed stars. Planets were identified as different from stars because they changed their position over time, whereas the stars were seen to be eternally fixed in place. The Earth-centric model stood the test of time for over 1,500 years. It wasn't until the 16th century that things started to change when Nicholas Copernicus proposed to put the sun at the center of the solar system. In so doing, he put the Earth into rotational motion about an axis, and he put the Earth into revolutionary motion around the sun. But putting the Earth into motion was hard to swallow for most people. Copernicus's idea didn't really start to take hold until the early 17th century, when considerable evidence for the Copernican model was compiled by the likes of Tycho Brahe, Johannes Kepler, and Galileo Galilei. Tycho Brahe, with mural quadrants, sextants, and his naked eye, used parallax measurements to find distances to the planets. He focused on Mars and tabulated volumes of data on a daily basis. Using this information, Kepler found that the orbits of the planets, including the Earth, were ellipses. And Galileo, using the newly invented telescope, discovered that the Milky Way cloud was actually stars, that the sun had spots on it that indicated that the sun was rotating, that Venus has phases like the moon, indicating that it goes around the sun, and Jupiter has 4 moons. Imagine how it must have felt when Galileo first saw these moons. All the world believed that everything revolved around the Earth, and here you are looking at moons that are orbiting Jupiter, not the Earth. But resistance to change is strong, and it wasn't until the 18th century that Newton turned the tide for good. We are all familiar with his formula that force equals mass times acceleration. Newton's better understanding of gravity was the key. A good way to view gravity is to think of it as a gravitational field surrounding the object. The intrinsic strength of the field is set by the fixed mass of the object. But as you can see in this illustration, when distance from the object increases, the surface area over which the field is spread increases as well. This effectively weakens the force of gravity felt at the more distant point. We know that the geometry for a sphere has the increase in surface area proportional to the square of the radius. So the gravitational field strength is reduced by a factor of 4 every time the distance increases by a factor of 2. We call this the inverse square rule. We'll see this rule again when we discuss standard candles in our section on stars. It's interesting to note that the constant of proportionality, g, in Newton's universal gravitation formula was not known to Newton. It took another 100 years before physicists had instruments sensitive enough to measure this number. But once we had it, it became possible to measure the mass of the Earth at 6,600,000 trillion tons. Newton broke Aristotle's 2,000-year-old dictum that there are 2 sets of rules for nature. One set for here on Earth, and another set for the heavens. With Newton, we came to understand that there is only one set, and it applies everywhere. In 1752, the French astronomers Lalande and Lacaille used the parallax method to calculate the distance to the moon. Here's how it works. 1. Draw a line from a point on Earth to the moon directly overhead. 2. Extend this line to a distant star. 3. From a measured distance across the Earth, draw another line to the distant star, and another one to the moon. Measure the angle between these two lines. In our example, it's approximately 1 degree. This is the parallax. Note that this line to the moon crosses two parallel lines drawn out to the distant star. From simple geometry, we know that the parallax angle theta is also the angle between the two lines at the moon. Now we have all the angles of the Earth-Moon triangle, and we know the length of one side. Simple geometry gives us the rest. Our parallax calculation gives us 226,467 miles to the moon. Of course, the moon travels in an elliptical orbit around the Earth, so its distance varies. Here's how different full moons look between the closest and furthest points. An interesting note on distance is that once you know the distance, there are a number of other things we can learn about an object. For example, given the distance r and the angular displacement of the object in the sky, we can calculate its size. Here we see the moon's diameter is 2,174 miles. Here we are, on the surface of Mars. Mars is the furthest planet from the Sun, where a person can actually find dry land to stand on. This is the photograph taken by Curiosity that's currently roaming around the surface of Mars, digging into the surface, looking for water, past signs of life. It's April 2013. About midday, and the temperature is just about freezing. In a few hours, it'll drop to 100 below. So, I better go find some shelter. Given the orbits of Mars and the Earth are ellipses, and their total velocities are different, the distance between the two can vary from 34 to 250 million miles. Back in 2003, the two planets reached a near minimum distance of 35 million miles. The last time that they were that close was over 50,000 years ago. Rather than list all the ranges of distances between the Earth and the various planets, a good way to report planetary distance is to use an average distance from the Sun. For Mars, it's 142 million miles. Mercury, a hot cratered rock, not much bigger than the Moon, is only 36 million miles from the Sun. Venus, with its sulfuric acid atmosphere and surface temperatures that can melt lead, is 67 million miles from the Sun. Jupiter, the largest planet by far, is 483 million miles from the Sun. We'll come back to Jupiter in a minute. Saturn, with its beautiful rings, is 886 million miles from the Sun. Uranus, with its extremely cold hydrogen and helium atmosphere, is 1.78 billion miles from the Sun. Neptune, a veritable twin of Uranus, is the furthest planet from the Sun at 2.79 billion miles. Pluto, as with other dwarf planets, is in the Kuiper Belt at 3.66 billion miles from the Sun. Let's take a closer look at Jupiter. It is the giant solar system vacuum cleaner, eating up the Sun's early debris to become larger than all the rest of the planets combined. An example of this was the comet Shoemaker-Levy colliding with Jupiter in 1994. The first impact occurred on July 16th, when fragment A of the nucleus entered Jupiter's southern hemisphere at a speed of 37 miles per second. Instruments on the nearby Galileo spacecraft detected a fireball plume that reached a height of almost 2,000 miles. Remember that our atmosphere extends only a few hundred miles above us. Over the next 6 days, 21 distinct impacts were observed, and the largest coming on July 18th. This impact created a giant dark spot over 7,500 miles across. The whole Earth could fit into the mark. The Jupiter-Sun gravitational system sets up an interesting phenomena called Lagrange points. In 1772, French mathematician Louis Lagrange discovered 5 points around orbiting objects where gravitational and centripetal forces cancel themselves out. Lagrange claimed that small objects could orbit these Lagrange points. 134 years later, 4 such minor planets were found around Jupiter's L4 and L5 points. Take a look at the asteroid belt, and you can see swarms of asteroids in the L4 and L5 points for Jupiter. In L4, these are called Trojan asteroids. In L5, they're called Greeks. In 2010, we discovered a Trojan asteroid orbiting Earth's L4 point, 60 degrees ahead of Earth, called 2010 TK7. Here we see an animation of 2010 TK7's orbit. The clock at the upper left shows how the orbit changes over time. Over the next 10,000 years, it will not approach Earth any closer than 12.4 million miles. That's 50 times further away than the Moon. Our space program takes advantage of these points when we position satellites to observe the Sun. We'll cover this a bit more in our section on the heliosphere. We'll also see Lagrange points in our discussion of binary star systems because they play a key role in their evolution into supernova, a key rung on our distance ladder for distant stars and galaxies. The Kuiper Belt is a region of the solar system beyond the planets, extending from the orbit of Neptune to 5.1 billion miles from the Sun. It is similar to the asteroid belt, although it is far larger, 20 times as wide and 20 to 200 times as massive. The Sun is the final object we'll cover. It defines the entire solar system, but figuring out how far away it is difficult. This is because we cannot see any nearby stars for parallax measurements. The Sun is just too bright. But total eclipses and passages of Venus across the face of the Sun as viewed from Earth have enabled excellent measurements. Here is a method that uses parallax to find the distance to Venus, that in turn enables us to triangulate the distance to the Sun. Let's look at the motion of Venus in the sky relative to the Earth. As Venus orbits the Sun, it gets further away from the Sun in the sky, reaches a maximum separation from the Sun, corresponding to the greatest elongation, and then starts going towards the Sun again. Now, by making observations of Venus in the sky, one can determine the point of greatest elongation. At this point, the distance between the Earth and Venus can be measured by a parallax. It's 64.6 million miles. The line joining Earth and Venus will be tangential to the orbit of Venus. Therefore, a line from Venus to the Sun at this point of greatest elongation is 90 degrees from the line between Earth and Venus. Drawing the line between the Earth and the Sun fills out the triangle. We call the length of this line, that represents the distance between the Earth and the Sun, an astronomical unit, or AU for short. The angle at the Earth is easily measured. It's 46 degrees. Now, using trigonometry, one can determine the distance, AU. It's 93 million miles. Once the distance between the Earth and Sun is known, one can calculate a number of other parameters. We know that the Sun subtends an angle of just over 1/2 of a degree. As we did with the Moon, we can calculate the diameter of the Sun at 860,000 miles. The surface area at 2.3 trillion square miles, and the volume at 330,000 trillion cubic miles. The Earth's orbit is very close to circular. So, with the Earth's orbital radius around the Sun being 93 million miles, the distance traveled in a year is the circumference of the circle, 584 million miles. Dividing that by 1 year, we get the velocity of the Earth around the Sun at 66,700 miles per hour. Now, with the distance of the Sun and our velocity around the Sun known, we can use Newton's equations to calculate the mass of the Sun at 2.2 billion trillion tons. In fact, the Sun is 99.98% of the entire mass of the solar system. So as vast as the planet Earth is, over 1 million Earths can fit into the Sun. So, how long does it take light from this magnificent Sun to reach the Earth? Until early in the 18th century, it was generally believed that the speed of light was infinite. This view was held by Aristotle in ancient Greece and vigorously argued by the French philosopher Descartes, and agreed to by almost all the major thinkers for over 2,000 years. Galileo was an exception, but when he tried to measure the speed of light, he failed. Light was either too fast or possibly infinite, was his conclusion. But Galileo did set the stage for the first measurement. After he discovered the first 4 moons of Jupiter, he suggested that the eclipse of the moon Io would make a good celestial clock that navigators could use to help determine their location. In 1676, the Danish astronomer Ole Romer was compiling extensive observations of the orbit of Jupiter's moon Io to see if Galileo was correct. The satellite is eclipsed by Jupiter once every orbit. Timing these eclipses over many years, Romer noticed something peculiar. The time interval between successive eclipses became steadily shorter as the Earth in its orbit moved towards Jupiter, and became steadily longer as the Earth moved away from Jupiter. In a brilliant insight, he realized that the time difference must be due to the finite speed of light. That is, light from the Jupiter system has to travel further to reach the Earth when the 2 planets are on opposite sides of the Sun than when they are closer together. Using what he knew about planetary orbits from Kepler, he estimated that light required 22 minutes to cross the diameter of the Earth's orbit. The speed of light could then be found by dividing the diameter of the Earth's orbit by the time difference. The actual math was done by others after Romer's death in the early 1700s. Those who did the first arithmetic found a value for the speed of light to be 141,000 miles per second. Not too bad for the instruments of the 18th century. The modern value is 186,000 miles per second, as determined by bouncing laser light off the moon. So to answer our question about how long it takes light from the Sun to reach the Earth, we simply divide the 93 million miles to the Sun by 186,000 miles per second to get 8.3 minutes. In this segment, we built the second rung of our distance ladder, parallax. We can now use the diameter of the orbit of the Earth around the Sun as our baseline, 186 million miles. Combined with direct measurement and geometry from the first rung, we are set to measure distances to the stars. But first, we'll close out our chapter on the solar system by taking a look at the heliosphere. So doing, he put the Earth into rotational motion about an axis, and he put the Earth into revolutionary motion around the Sun. But putting the Earth into motion was hard to swallow for most people. Copernicus's idea didn't really start to take hold until the early 17th century, when considerable evidence for the Copernican model was compiled by the likes of Tycho Brahe, Johannes Kepler, and Galileo Galilei. Tycho Brahe, with mural quadrants sextants, and his naked eye used parallax measurements to find distances to the planets. He focused surrounded by a number of celestial spheres that rotated around the Earth each day. There was a sphere for the moon, one for the sun, one for each planet, and one for all the fixed stars. Planets were identified as different from stars because they changed their position over time, whereas the stars were seen to be eternally fixed in place. The Earth-centric model stood the test of time for over 1,500 years. It wasn't until the 16th century that things started to change when Nicholas Copernicus proposed to put the Sun at the center of the solar system, installed on Mars, and tabulated volumes of data on a daily basis. Using this information, Kepler found that the orbits of the planets, including the Earth, were ellipses. And Galileo, using the newly invented telescope, discovered that the Milky Way cloud was actually stars, that the Sun had spots on it that indicated that the Sun was rotating, that Venus has phases like the Moon, indicating that it goes around the Sun, and Jupiter has 4 moons. Imagine how it must have felt when Galileo first saw these moons. All the world believed that everything revolved. Look up at the night sky. See the stars move across the sky. The moon and the sun do the same thing. They rise and set. It's not surprising that ancient peoples viewed the earth as fixed, and all celestial objects revolved around us. The ancient Greeks, such as Plato, Aristotle, and culminating in Ptolemy, constructed a cosmology with the Earths around the Earth. And here you are looking at moons that are orbiting Jupiter, not the Earth. But resistance to change is strong, and it wasn't until the 18th century that Newton turned the tide for good. We are all familiar with his formula that force equals mass times acceleration. Newton's better understanding of gravity was the key. A good way to view gravity is to think of it as a gravitational field surrounding the object. The intrinsic strength of the field is set by the fixed mass of the object. But as you can see in this illustration, when distance from the object